Hello everyone, this is lecture 5 for the atomic physics. In the last lecture we were discussing about the questions regarding Bohr's model, and today also we'll discuss some more questions because this is a very important topic from the exam point of view. So let's see, calculate the wavelength of the first 4 lines of the Lyman series of the positronium on the basis of the simple Bohr's theory. So what is positronium? Positronium is simply a positive electron, means kind of charge having positive, and it is the center of the atom. And you have this positronium, and you need to calculate the wavelength of the first 4 lines. That is means transition from first excited state to ground state, then second to first, and that's how. So L alpha, L beta, L gamma, and Z will be 1. So first you need to calculate the reduced mass. So there will be one electron and one positronium. So this is a system, atomic system, and now reduced mass will be same. They will both have the same mass but different charges, that is plus and minus. So reduced mass will be mm divided by m plus m. This will give you m by 2, and mu by m will be equal to 1 upon 2. So you already know that why we are calculating the reduced mass. So we already discussed this in detail. Now different energies for different orbits. So for the first orbit or the ground state, we will have minus 13.6 divided by n square, and z is 1. So z square will give you 1 here. Multiply mu by m will give you the exact energy, that is 1 upon 2. So this will be minus 6.8. Similarly, you can find the for the second orbit or the first excited state, that will be minus 1.6, and just 2 square, 3 square. That's how you can calculate this. And simply you don't need to calculate these all energy values. You can directly use this formula, 1 upon lambda equal to r infinite mu by m, 1 upon n final square minus n upon 1 upon n initial square. So that's how you can calculate all the wavelengths, L alpha, L beta, L gamma. And but you can also use this method also, means now you have energy for all orbits. So E2 minus E1 will give you the transition energy for the first L alpha, and similarly for 3 to 1 will give you L beta, and 4 to 1 will give you gamma. And when you have the energy, you can calculate the frequency directly. That will be energy divided by the h, Planck's constant, and you can calculate the lambda using this formula. So you can use either this method or this method. So let's see the next question. For muonic atom, mu, mass of muonic atom is given as 207 mass of electron. We need to find the energy expression. We need to find the calculate energy, frequency, wavelength of L alpha, L beta, and H alpha lines. So we know this is your muonic atom. So means there will be positive charge here and one electron system. Now this is kind of hydrogen-like system. So we know charge is plus 1 and Z is also 1. So mu is given 207 me, and we can calculate the reduced mass, that will be mu equal to mu, me, and mu plus me. This will give you 207 by 208 me. Now this is your reduced mass, so you can just use this formula, 1 upon lambda equal to r infinite mu by m, 1 upon square minus 1 upon 2 square. So you can use directly this formula, and now you can calculate the lambda L alpha and lambda L beta, L beta L alpha. And for the H alpha is nothing but there is a Balmer series, means transition is occurring to the final state will be first access state, that is n equal to 2. So 3 to 2, that will give you H alpha. So that's how you can calculate directly. You just need to use these formulas and you can calculate very easily. So always remember this thing, the reduced mass thing, and you can solve all kind of questions. So next question is, the emission spectrum of hydrogen atoms is taken with a diffraction grating, line spacing d equal to 2 micrometer. A line of Balmer series is observed in the second order at an angle theta equal to 29 degree 5 minutes. What is the quantum number of excited state from which the transition starts? So there will be, so here what is given is there is this grating. Grating is nothing but there are some opaque spaces and the transparent spaces where light can go, and this is called the line spacing, that is the distance from the center of this vacancy and center of this vacancy. So you can see this. Now this distance is called the line distance or line spacing. So we'll use a Bragg's law here. You know this formula, d sin theta equal to n lambda. This will give you the conjunctive interference, means the maximas. So now you can just use d here directly. This is this distance, and this is already given, and that is equal to 2 micrometer. So you can show this, means this is spacing either by d, e plus d, or a plus b. So here d is given, so we will just use that d. So here if you see that how it is d plus e, so if you call this distance as d, then this is e, and this half will be e by 2, and this half will be e by 2. So e by 2 plus e by 2 will give you e and d. So d plus e will be your total distance, and here this d represents this e plus d. Okay, so these are the same terms. So d is given, just substitute the value 2 micrometer, and theta is given 29 degree 5 minutes, and you know this is second order, so you will use 2, and you can find the lambda. So now you have lambda, you need to find that from where the transition starts and end at the second, means second orbit. So you'll use this formula. You have lambda, you know this r infinite, 1 upon 2 square minus 1 upon n square. you can calculate the n, that is equal to 4. Now next question is, a mu meson, which is 210 times mass of electron, is captured by a proton to form hydrogen-like atom. Now again, hydrogen-like atom is formed by the mu meson, and now what we need to calculate is energy emitted when mu meson falls from the first excited state to the ground state. So transition from 2 to 1, and we need to find the energy. So how can you find the energy? So you know this formula, that is, first you need to calculate the reduced mass, that is mu plus mp, because this is the hydrogen like now formed. This proton captured this mu meson, so now it will be mu mp, and we already know what is mass of meson is 10 times me, and the mass of proton is nothing but 1836 times mass of electron. So this will give you reduced mass, that will be 188.45 mass of electron. Now energy is given by R infinite Sc, and now this is your mu by me factor. You already know how it came. So 1 upon 1 square minus 1 upon 2 square, this is your transition. So this will give you your energy, that will be 1922 electron volt. Now if you need to calculate in the second part the radius of the first Bohr orbit, so that will be again 0.52 divided by mu by me. So mu by me you already calculated, that is 188.45. So it will give you the first Bohr orbit radius, and velocity will remain same, that will equal to z alpha c by n, and alpha is nothing but 1 upon 137. So this will z is 1 here, so it will be this will be your velocity. Now next question is, hydrogen atom in its ground state is excited by means of a monochromatic radiation of wavelength 975 angstrom. How many different resultant lines are possible in the spectrum? So there is this transition occurring with the help of this radiation. This radiation is applied on the hydrogen ground state. Now how many lines will you get? So what you need to check that to what transition can occur, means excited. So for that, what we will do, we see that this is your ground state. Now this radiation is applied, which is of lambda 975 angstrom. Now you need to check that what can be the maximum n. So for that you just put this value, means if wavelength is given in angstrom, you can directly find the energy as 12375 divided by lambda in angstrom. This will give you energy in electron volt. You must remember this formula. Now energy will be 12.69 electron volt. Now you just substitute the value here, 12.69 equal to 30.7, and this is your transition. We need to find this n. So this n square came out to 15, so it must be 3, because if it is 16 only, then it is possible to 4, otherwise it can be possible only up to the 3. So now you have n equal to 3, so transition can occur only up to the 3. Now how many lines are possible? You can see that it can go from 3 to 2, or 3 to 1 directly, or 2 to 1. So only 3 lines are possible. Or there is this another formula you can directly use, that is n minus 1 divided by 2. So n is the maximum state. So it will be 3, will give you here 3 lines. So that is the case. Now second question asked here is, calculate the lambda longest. Assume ionization from hydrogen atom is this. So we need to calculate the maximum wavelength is possible. So for maximum wavelength you need to find the minimum energy. So minimum energy will be came from this, for this transition 3 to 2. So for this transition we will calculate the wavelength, that will be your longest wavelength. So that's how you can solve. Next question is, a doubly ionized lithium atom is hydrogen like atom, Z equal to 3. Find the wavelength of the radiation required to excite the electron in lithium from first to the third Bohr orbit. So here it is a doubly lithium atom, and this is doubly ionized, means 2 electrons are emitted, only 1 electron is in the orbit. So again it will form the hydrogen like atom, means charge will be 3 in the proton, but here you have only 1 electron, that's why it is forming the hydrogen like structure. So you can calculate the lambda simply, 1 upon lambda equal to R infinite, and transition is from the 3 to 1. So it will be 1 upon 1 square minus 1 upon 3 square Z square. So it is always there for the hydrogen, it just become 1. That's why we just ignore it. But here it is 3, Z equal to 3. That's why we need to apply here Z square. So lambda will be 113.7 angstrom for this transition. Next question is, ionization energy for hydrogen like atom is 4 Rydberg. Now this time ionization energy for hydrogen like, there is some hydrogen like atom, we don't know what is this, but that has the ionization energy as 4 Rydberg. And what is Rydberg? You must know that 1 Rydberg is equal to 1 R infinite Sc, that is 13.6 electron volt. So now it is 4 Rydberg. And lambda for radiation emitted when electron jumps from first excited state to the ground state. So 2 to 1 transition is given. So we need to find what is the lambda. So see, we use this formula, 1 upon lambda equal to this is Z square R infinite, means this is your simply, see, this is your ionization energy formula, E1 equal to minus 30.6 divided by 1 square Z square. And in place of E1 we have 4 Rydberg, that is 4 multiplied by 13.6. You just compare, this will give you Z equal to Z square equal to 4 and Z equal to 2. That's why in place of Z square we are using this formula, and we place here Z square as 4. So that's how you can solve, and you can find the lambda here. That will give you the value. And the next part they asked, Also calculate the radius of the Bohr orbit. So for the Bohr orbit, we know the formula n square by z, and z equal to 2 here and equal to 1, so it will give you r naught by 2, that is 0.52 by 2 angstrom. So this will be your Bohr's orbit radius. Next question is, a single electron orbit surrounds a stationary nucleus of charge plus Ze. It requires 47.2 electron volt to excite the electron from the second Bohr orbit to the third orbit. We need to find Z. So we know this is a simple formula. Means for this transition 3 to 2, the energy is already given, that is 47.2. So RSC is nothing but 13.6 and Z square. So from here Z square will be, means Z can be calculated, that is equal to 5. Now next, energy emitted during transition from 4 to the 3. So again we already know the Z, we just calculated, so we can just use directly the formula. 13.6 Z square is 5 square. 1 upon 3 square minus 1 upon 4 square will give you 16.53 electron volt. This is energy is required for the transition. Next is energy required to free electron to infinity. So that is the total energy it is consuming, means having the maximum energy. That is for the ground state. So minus 13.6 divided by n square, that is 1 square, multiplied by z square. This will be your total energy. So this minus 340. So 340 electron volt energy is required to emit the electron to the infinity. Now if you need to calculate the lambda of that radiation, that will be 12357 divided by the energy in electron volt to give you the lambda in angstrom. So you must remember this formula. This angstrom will give you electron volt and electron will give you in the angstrom. So that's how this works. Next is find kinetic energy and the potential energy. So we know what is the kinetic energy. So kinetic energy is nothing but simply the mode of total energy. So total energy is this. There will be 340 electron volt, and potential energy is nothing but twice the total energy. That will be twice multiplied by minus 340. This will give you your potential energy and kinetic energy. Now next is find Bohr orbit radius and its angular momentum. So we need to find this. So we know the formula, 0.52 divided by z, n square is 1, so it will give you this. This will be your radius. Angular momentum is nh by 2 pi, so n is 1, so h by 2 pi is nothing but h cut. So this will be your angular momentum. And that's all for the Bohr's model. The next we will start the Sommerfeld model, and thank you everyone.